6.6 logarithmic and exponential equations. So what we're going to be doing today is going to pull a lot from 6.5. So these properties right here, we're going to use these to solve, okay? Alright, so example 1, we want, well, before we do that, sorry, just as a reminder that y equals log base a of x is the same thing as x equals a to the power of y. Remember, that's how you would switch it. And that if we have the same log and only one log on each side, we can go ahead and get rid of them. But they can only be same log equals same log. No pluses, no minuses, just one log equals one log. Alright, so as we approach this, we kind of want to work with each side by themselves and kind of see if we can simplify each side. So we can simplify because we know we can move this number over here using property 5. So what am I referring to? Property 5, the number 5. If you go back to this chapter, that's property 5, where the exponent can go in, or the number in front can be the exponent and vice versa. Alright, so let's go ahead and do that. We have log base 5 x squared equals 9, or equals log base 5 9. So you see how it's single log equals single log, and they're both the same bases. We can actually get rid of them. So we're left with x squared equals 9. We take the square root, so we get x equals positive negative 3. Now that's not our answer, because remember, logarithms, they have a special domain. There's restrictions on the domain. So before you think you're done, you actually always need to find the domain. So to find the domain, we set the argument, or whatever x is, greater than 0. So we have x is greater than 0. So that is the domain. So if we have x equals negative 3, and then we have positive 3, we have to compare them. Is negative 3 greater than 0? No. So that's not a solution. Is 3 greater than 0? Yes, it is. So our only solution is positive 3. Alright, example 2. So you want to treat each side individually. So let's look at the left side, look at the right side, try to simplify, try to combine, right? It's just like combining like terms, except we have a little bit of different rules. So we see how that's log 5. That means they're the same, so we can combine like terms, and we can combine them because they're adding. So remember, if they're adding, that's property 3. So I'll go back and show you. This is the last time I'll go back and show you. So property 3, right here, if they're adding, they're actually multiplying. So we can put them together using multiplication. We have log 5, x plus 6, times x plus 2 equals 1. Now we can actually simplify more because we can FOIL. So we have log base 5, x squared plus 8x plus 12, ooh, that's small, equals 1. Alright, now that we're here, we only have one logarithm. Whenever you have one logarithm, switch it to exponent. So you see we only have one logarithm here. The whole thing, it's only one logarithm. So switch it to exponent. So we have 5 to the power of 1 equals x squared plus 8x plus 12. We know what 5 to the power of 1 is. It's 5. And since we have a quadratic, we want this to equal 0. So we're going to subtract 5 to both sides. And when we do, we have 0 equals x squared plus 8x plus 7. Now we factor. So we get x plus 7 and x plus 1. We set each factor equal to 0. We subtract 7 from both sides. So we have negative 7 equals x. and then we subtract 1 from both sides to get negative 1 equals x. So those are our proposed solutions. But before we decide that it's actually a solution or not, we need to check that domain. So to check that domain, we set the argument greater than 0. So here in the original equation, we actually have two arguments. We have x plus 6 is greater than 0, and x plus 2 is greater than 0. So we have x has to be greater than negative 6, and x has to be greater than negative 2. Whenever you have two domains, it's not both are the answers. The domain is the highest number. So it's your largest number, your highest number, your largest value, your biggest value. So this is actually our domain. The reason being is because we need to make sure it works for both arguments. So whatever we plug in, it needs to work for both of them. If it doesn't work for both of them, it won't work for all of them. Meaning, okay, so keep up with me. I'm not going to write it down, but I'm going to talk you through it. Let's hypothetically say, x is negative 7. That's not a hypothetical, it's true. X is negative 7. So if we put negative 7 here, it's not greater than negative 6, and it's not greater than negative 2. So it's not a solution. And if we do negative 1, so negative 1 is greater than negative 6, negative 1 is greater than negative 2, so our only solution is negative 1. All right. Example 3. So again, anytime we have multiple logarithms, we want to try our best to make it one logarithm. We're combining like terms, as we say. So if we look at the left side, I can't do anything there. But on the right side, I actually can combine them because they're minusing. So because they're minusing, we can actually divide them. So we'll have ln x plus 6 over x minus 4. My bad, ln x. Forgot that x. Let me rewrite that. Alright, do you notice that they both only have ln on each side? That there's only one logarithm on each side? So because we have that, we can cancel them out. So we have x equals x plus 6 over x minus 4. Anytime we have a fraction, we need to get rid of it, and the only way to do so is by multiplying by the denominator. Technically, all we're doing is just moving it to the other side. So we have x minus 4 times x equals x plus 6. We're going to go ahead and distribute the x. So we have x squared minus 4x equals x plus 6. We have another quadratic. So since we have another quadratic, we need to make this equal to 0. So we're going to subtract x to both sides. And then we're also going to subtract 6 to both sides. So we're left with x squared minus 5x minus 6 equals 0. We can go ahead and factor this into x minus 6 and x plus 1 equals 0. That means we have x minus 6 equals 0 and x plus 1 equals 0. Or if we solve for x, we have x is 6 and x is negative 1. Again, those are our proposed solutions, but we don't know if they're true or not. It's possible to have a no solution, it's possible to have one of them, or multiple solutions, okay? So let's go ahead and check our domain. So we have two arguments. We have x plus 6 is greater than 0, and x minus 4 is greater than 0. So we have x is greater than negative 6, and x is greater than 4. So this is our domain. It's the biggest number is 4. So let's compare our solutions. Is 6 greater than 4? It is. 6 is greater than 4, so it is a solution. Is negative 1 greater than 4? It's not. So if you would have not known that the only domain is 4, so say you said both of these are the domain, negative 1 is greater than negative 6, right? It is. But is it greater than 4? No. So that's why we go with the biggest number. So our only solution is positive 6. It is not always the biggest number that is going to be the only solution. So you see here how we have negative 7 and negative 1, and the answer was only negative 1? That is a bigger number, right? But that's not why it's the solution. Same reason right here. Just because 6 is bigger than negative 1 doesn't make it a solution. It's just coincidental that it's been happening that way.
Examples 4 through 6 are going to help us with change of base and how do we solve things that we can't use change of base for. So I have a little like when to use change of base or the ln method. Now it's not actually called the ln method, that's just what I call it because that's what we do. You'll see as we go through that it's just like you just throw ln. You'll see what I mean. So when to use change of base or the ln method, you cannot solve as exponents, meaning you can never achieve the same base. So like we were doing in 6.3 where we had to get the same base like 2, 3, or 4, if you can't do that, you need to use change of base or the ln method. When to use change of base? When there is one variable as an exponent, when there is no plus or minus next to a singular variable as the exponent. So like example 4, we could use change of base there because there's no plus or minus and there's only one exponent. Example 5, there's multiple exponents that are variables and there's pluses and minuses. So example 4, we would use change of base. Example 5, we would use the ln method. When to use the ln method? When you have multiple exponents that contain a variable that contain variables, when there's a plus or minus next to any exponent that is a variable. So example 4, you don't need to use the ln method because it's just a singular variable, but if we go again to example 5, there's multiple variables as exponents and there's pluses and minuses next to them. That's when we would use the ln method.
All right, so we need to solve using, we need to solve. And we can't really solve here because can I get the same bases? Can 5 and 3 ever be the same base? They can't. So I need to switch this to logarithm. But how the heck can I even switch this to logarithm when there's multiple exponents? I make it a logarithm. So what we do is we add ln to the front of each of these. Remember, in math, I'm allowed to do anything I want as long as it's fair. So if I add it to both sides, they can actually cancel each other out. So it's fair. So if we do it to the left side, you have to do it to the right side. Now I have a logarithm. Okay, that's our first step. Now let's just work with our logarithms. If we see an exponent, we usually move it to the front. So let's move it to the front. Okay, we did that. Now, anytime we see parentheses and something outside, what do we usually do? We usually distribute, and that's exactly what we're going to do. So when we distribute, we actually can't distribute because it's x times ln3, so you just write it next to it. We have x ln5. I accidentally said ln3, but you get it. And then we have 3 ln5 equals 2x ln3 minus 5 ln3. Excuse my dogs barking. I can't lock them up. Alright, now we're trying to solve for x here. So if we have multiple x's in multiple places, we need to move anything with an x to one side and anything without an x to the other side. So you see here how we have something with an x? I want to move it over. So when we do, we have x ln 5 minus 2x ln 3 plus 3 ln 5, and that equals negative 5 ln 3. This does not have an x, so I don't want it over on the x side, so I'm going to move it over. And now when we do, we have x ln 5 minus 2x ln 3 equals negative 5 ln 3 minus 3 ln 5. All right, next step. Every time you move something over, remember when we were doing the inverses and you had like xy minus y, you factored out that y. We're going to do that here. We're going to factor out the x because they have it in common. So when we do, we're left with ln 5 minus 2 ln 3 equals negative 5 ln 3 equals minus 3 ln 5. And now our last step here is going to divide. So we have to divide by ln 5 minus 2 ln 3. And when we do, we finally have x. We have x equals negative 5 ln 3 minus 3 ln 5 over ln 5 minus 2 ln 3. That's the exact answer. Let's do approximate. So I'm actually going to show you how to plug this into your calculator because it can be pretty tricky. All right, let me switch screens. All right, so if you have a newer calculator, I'm going to show you how to do it. If you have an older calculator, I'll still show you how to do it. So if you have a new fancy calculator and you can, press alpha y equals enter. We get our fraction bar. So on top we have negative 5 ln 3, so ln is right here. And then minus 3 ln 5. And on the bottom we have ln 5 minus 2 ln 3. And press enter. And we have our approximate solution of 17.56. I'll write it down afterwards. If you don't have that alpha y equals option, you can download this calculator I'm showing you on my screen right now. You can actually download it. If you go to announcements, I have an announcement on how to download it. Texas Instrument is offering it for free. Usually this is not free. It costs like $100 a year to have the license, but they're giving you 6 months for free. So download it if you don't have a calculator. If you have an older calculator, you just have to do it step by step. So let me show you how to do that. So if you have an older calculator, we do the top first. So negative 5 ln 3 minus 3 ln 5. Hit enter. And then we have to hit divide parentheses because we have multiple things in the bottom. So we hit those parentheses. We do ln 5 minus 2 ln 3. And see how we get the same exact answer. All right. All right, so we have our approximate solution of 17.56. That's our approximate. So anytime you have multiple x's as exponents, multiple variables in the exponents are like things happening to the x, you have to do it this way. I call it the ln method. It doesn't, that's not the name, that's just what I call it. So you see the difference here, all the way at the bottom of the screen in example 5, it's just one variable, nothing's happening to the x, so we don't treat it this way. We don't. There's an easier way to do it. All right, let's do example 5. So example 5, I cannot get these to be the same bases. 2 and 5, I can't have those be the same. 2 to the power of anything does not equal 5. It's going to be a decimal. We don't know it. So let's switch it to logarithm. We have log base 2 of 5 equals x. Now we do change of base. So change of base, you can use ln or log. It does not matter. For this one, I'll use log. For b, I'll use ln. So we have log 5 over log 2 equals x. That's our exact answer. And plug that into our calculator, we get about 2.32. All right, let's do B. So you see how that's 8 times 3? Why would they have that? Why wouldn't it just be 24? Because you have to divide it. Because this 8 is not actually attached to the 3 to the power of x. So let's divide it out. Always do that if there's a number in front that looks like that. Get rid of it. So we have 3 to the power of x equals 5 over 8. Since there is no way I can get 3 or 5 over 8 to have the same base, I need to switch it to log. So we have log 5/8. My bad. Log base 3 5/8 equals x. Now we do change of base. So you can use log or you can use the ln. It doesn't matter for change of base. So I'm going to use ln for this example. We have ln 5 over 8 over ln 3 equals x. That's our exact solution. Our approximate solution is negative 0.43. And the reason why it's negative is because, isn't it a fraction? Yep, that's why it's negative. Alright, example 6. So example 6, do you think we can use change of base? Or do you think we have to use the ln method? We have to use the ln method. Why can't we do what we did in example 5? Why can't we use change of base? It's because we have multiple exponents with variables. And we're doing stuff to those exponents. Okay. Alright, so what we're going to do first is put an ln in front of both of them. Follow the steps exactly example 4. So example 4, you see how we added the ln in front? The next step was to distribute. Literally every step is the same. Alright, so we're going to move that to the front, our exponent to the front. So we have x minus 2 ln 5 equals 3x plus 2 ln 3. Just like before, we go ahead and distribute. So now we have x ln 5 minus 2 ln 5 equals 3x ln 3 plus 2 ln 3. Alright, just like before, anything with an x goes to one side, anything without an x goes to the other side. So what I'm going to do is subtract 3x ln 3. And when we do, we have x ln 5 minus 3x ln 3 minus 2 ln 5 equals 2 ln 3. This does not have a variable in it. Get rid of it. Move it to the other side. So we're going to add 2 ln 5, my bad. And when we do, on the left side, we have x ln 5 minus 3x ln 3 equals 2 ln 3 plus 2 ln 5. Take out the GCF. And then we divide. So after we divide, we get our exact answer of x equals 2 ln 3 plus, 2 ln 5 over ln 5 minus 3 ln 3. We are almost done here because we can simplify one more time. I don't know if you see it, but they both have a 2 in common, so we got to take it out. So when we do, we have 2 times ln 3 plus ln 5 equals, over ln 5 minus 3 ln 3. That's our exact answer for x. You can plug it into your calculator, and it is approximately negative 3.21.
Example 7. Solving an exponential equation that is in quadratic form. So there's this thing called u substitution. and it is so important in trigonometry and up. And today we're going to just get an introduction on what does that mean. So we have 3 to the power of 2x plus 3 to the power of x minus 30 equals 0. I know that this is a quadratic form because it's squared. It's 3 squared x. It's 3 to the power of 2x. So our goal is to make everything kind of start to look the same. What does that mean? Well, I'm just going to start writing and you'll get what I mean. We can change 3 to the power of 2x. We can actually change that to 3 to the power of x all to the power of 2, because, right, you just distribute it back. It's the same thing. And that's plus 3 to the power of x minus 30 equals 0. So now, do you notice that we have 3 to the power of x, 3 to the power of x? So what we're going to say is u is now 3 to the power of x. So let's substitute it in. We have 3 to the power of x, that stands for u, but don't forget we also have this squared on top, so squared, plus 3 to the power of x, which we know stands for u, all minus 30 equals 0. Now we just have a normal quadratic that we can factor. We can factor this into u. We're going to use different signs because it's minus 30, and we use 6 and 5. 6 times 5 is 30, 6 minus 5 is 1. We solve for it, we get u plus 6 equals 0, u minus 5 equals 0, so we have u equals negative 6, and u equals 5. Now, there is one stipulation here, is that when we plug it in, like hypothetically, if you plugged it in, that's negative 6. You know negatives mean fractions as exponents. So we can't use this because that'll create a fraction, and there's no fractions here. It's all normal numbers with exponents. The rule is your u must be greater than 0. Because of that, we know this is an extraneous solution, so right now the only solution we have is u equals 5. However, don't forget you did something. We said u is something special. U is 3 to the power of x, and that equals 5. They have 3 and 5 as a base. I cannot get them as the same base, so we use change of base. So change of base, we have ln 3 over ln 5 equals x.